Hi everyone, welcome to our third video for week 1 on frequency, frequency tables, and levels of measurement. So let's talk about data, calculations, and levels of measurement. To do that, we're going to start by introducing rounding rules. The first two biggies: round answers to one place more than the original data. So if you have whole numbers in your data list, your final answers should have one place past the decimal. And the last one's kind of a general math class rule. Don't round until the last step if possible. That prevents rounding error. If you're in a situation where you absolutely have to round in the middle because you can't carry your answer down, you should round those intermediate numbers to twice as many decimal places as you want in your final answer. So if our original data is whole numbers, we want our answer to have one decimal place. Our middle numbers should be rounded to 2 decimal places. If I want my answer to have 2 decimal places, those middle numbers should be rounded to 4 decimal places. So twice as many decimal places as you want in your answer. Quick review of rounding. If I want to round to the 10th place, I look at the number in the 100th place. So I want 8.75 to be 8 point something. If the number next to the place I'm interested in is 5 or higher, I round up. So I want to round to the 10th place. The thing behind the 7's a 5. I'm going to round that 7 up to an 8. So 8.75 becomes 8.8. If the thing next to the 7 is less than 5, we round down, meaning the 7 stays a 7 and we drop everything behind it. So 8.74 would round down to 8.7. Please note, I don't deduct points on your test for rounding errors as long as you showed your work and your supporting work is correct. It is more important that you understand how to do the calculations than you know how to round when you get to the end. So important information, but don't stress over it. Quick review of levels of measurement. The level of measurement is determined by how the data was collected. The reason that's important is it affects what we can do with the data. Certain techniques require more information or a higher level of measurement. There are 4 levels: nominal, ordinal, interval, and ratio. We're going to talk about those 4 really quickly. So the first is the nominal scale. Data measured on a nominal scale is qualitative. So all of our categorical data generally falls here in the nominal scale. Eye color, blood type, favorite food, business names, type of pet. Ordinal scale is similar to nominal except for the fact that the ordinal data can be ranked. There is a meaningful ranking of some things being better than others. So examples are like top 5 local restaurants or 5-star rating systems, where my answers are word answers, but some of those things are better than others. Nominal is related to name. That's why it's categorical data. And ordinal is relating to position. That's what those words mean. And that indicates what those scales are measuring. I don't expect that you remember them, but it is good that you have seen them. We're going to start by looking at nominal scale data, and then we're going to work our way up. The next 2 are the 2 that we're going to see most consistently, and those are our numeric data, our interval scale, which is similar to ordinal except that there's a meaningful difference between data points. So this is definitely numeric data, but this is data that doesn't have a meaningful 0. The most common examples are temperature scales, Celsius and Fahrenheit. When we say 0 Celsius, that doesn't mean that there's no thermal energy in a system. right? That number was chosen arbitrarily as the freezing point of water, but that's not the freezing point of everything on planet Earth. Same for Fahrenheit temperature. There's a meaningful difference. We can arguably feel a 5% drop in temperature, or a 5 degree rather drop in temperature, but that 0 point is not helpful, and it makes it difficult to do comparisons. Words are hard today, I'm sorry. Ratio scale is the most common type of numeric data that we're going to see. Ratio scale is similar to interval, except there is a meaningful 0, so we can calculate ratios. This level of measurement gives us the most information. So this, again, is the most common type of numeric data we're going to see. So example, points scored in a basketball game, number of hours worked in a week. You can have 0 points scored in a basketball game. That has meaning in the real world, right? I can work no hours in a week, and that means something in terms of my pay. So these are things that have a meaningful 0, and I can talk about one score in a basketball game being double another, and that means something in terms of the data. Okay, so let's talk about something we are going to see a lot, frequency and frequency tables. So frequency is the fancy math term for the number of times a data value occurs. In other words, frequency equals count. Anytime you see frequency, we've counted something. So frequencies are whole numbers. 0 tells us that that data value is not present in the data set. 1 tells us the value occurs exactly once in the data set. A frequency of 2 tells me that value occurs twice in a data set. Relative frequency is the ratio of the number of times the values occurred to the total number of values in the data set. In other words, it's the percentage of the data set that one value makes up. It is usually expressed as a decimal, but can be expressed as an unreduced fraction or a percent. So for frequency, we're looking at how many times each data value occurs in the set. We're looking at the weight of each data value in the set. Remember, when we talk about ratio, we're talking about a fraction, which is why we use unreduced fractions. And the most common way to organize frequency is in something called a frequency table. So a frequency table, in some other books called a frequency distribution, is a tool that's used to organize a list of raw data. Typically we have 3 or 4 columns, depending on which type of frequency table or how much information we want to share with our readers. We should always have a data value or data range as the first column. So our categories or a list of numbers that we measured. The next column should be the frequency, how many of each data value showed up. So if I'm looking at, let's say, categorical variable of eye color, my first column would be eye color, so blue, brown, green, gray, other. My frequency would be the number of people with blue eyes or the number of people with brown eyes in my sample. That third column, which you usually do see included, is called the relative frequency. And the last column's optional, and that's cumulative frequency. And when you see cumulative in a math class, cumulative means a running total. So it's telling us we're going to add up some frequencies. So we're going to go ahead and construct a couple together. I'm going to show you examples of different types. So this example says 20 students were asked how many hours they worked per day. Their responses in hours are as follows: 5, 6, 3, 3, 2, 4, 7, 5, 2, 3, blah, blah, blah. I'm not going to read that all out. And they want us to construct a frequency table. So I know that I need at least 3 columns. I need one for the raw data, In this case, the number of hours worked. I need one for frequency, and then I need one for relative frequency. So let's start by filling out that hours worked column. My smallest number in that data set is 2, and my biggest number in that data set is 6. So I want a row that starts at 2 and goes all the way down to 6. And I'm going to count as I go. So I see 3 2s in my data set. So 2 has a frequency of 3. Move on to that next number, 3. I see 5 3s in the list. Moving on to 4, I see 3 4s. For 5, there are 1, 2, 3, 4, 5, 6 5s in the list. Ooh, there is a bigger number. There's a 7. There are 2 6s in the list, and then my eyes missed the 7. So there is 1 7 in the list. I'm going to add a row for the total, and I'm doing this because I know for that last column, relative frequency, I need to know what the total is. So remember, relative frequency is the ratio or fraction of the frequency for that value divided by the total frequency. So for our hours worked 2, my class frequency was 3, my total frequency was 20, so my relative frequency is 3 over 20, or 0.15. We're going to do that down the rest of the column. Take the class frequency, divide it by 20, spit out a decimal. So the next one's going to be 5 divided by 20, which I know comes out to 0.25. Next one is 3 divided by 20, or 0.15. 6 divided by 20, 2 divided by 20, and 1 divided by 20. I know if I add those fractions, I should get 20 out of 20. That's all of the data in my table. If I add those decimals, they should add up to 1, or 100%. And if you check, that actually does work out here. So we've likely filled out this table correctly. My frequency adds up to the number of students I was told I have. My relative frequencies add up to 1. So what we're going to do next is look at a cumulative frequency distribution, or cumulative frequency table. Remember that cumulative frequency is a running total for that frequency column, or relative frequency column. So we need to add a 4th column to our table. And you'll notice I've kept the totals down at the bottom. And then we're going to start with that first row. There's nothing before the first row to add, so that 0.15 is just going to come over. So the first row's cumulative relative frequency is 0.15. The next row, I'm going to pull that number down and add the new relative frequency to that. So 0.15 plus 0.25. So my new value is 0.40. And then I repeat. That value comes down, 0.40, and then I add the new value, 0.15. So 0.4 plus 0.15 is 0.55. And then we repeat. Pull the 0.55 down, add the 0.3, pull the 0.85 down, add the 0.1, pull the 0.95 down, add the 0.05. And you will notice when we clean that up, the very last row, our cumulative relative frequency is 1. And we should always see that as our last row. If you don't, something went wrong with either your relative frequency or cumulative relative frequency calculations. Because we know by that last row, we've accounted for all of the numbers in our list. That's 100% of our data. Okay, So this last example's already been completed for you, and I just want to talk about it briefly. The data shown in this table represents the height in inches of a sample of 100 male semi-professional soccer players. And what you'll notice in this table, because the heights of soccer players can vary so much, the data has been grouped into intervals or ranges or classes. So this first row represents people that are 59 to 61 inches. Yeah, 59.95 to 61.95. In the next chapter, we're going to talk about how to decide what those intervals should look like. But there are a couple things you should notice. There's a gap of 2 between the smallest and largest numbers in each interval. 59 to 61 is 2. 61 to 63 is 2. 63 to 65 is 2. You'll also notice the biggest value in one row becomes the smallest in the next row. In other words, we would say that these rows or intervals are contiguous, meaning they touch. They butt up right next to each other, and that's going to be important for a type of graph we're going to talk about in Chapter 2. Other than that grouping, this looks exactly like the other types of frequency tables. There's a count in the middle column that adds up to the total number we know we should have, a sample of 100 males. Here's our sample of 100. And the relative frequencies, if we add them up, adds to 1. All right, if you have any questions on frequency tables or how to read them, feel free to reach out. Otherwise, I will see you in our next video.